Welcome. This is Dr. Michio Kaku, professor of theoretical physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, we're going to summarize some of the latest news concerning natural catastrophes. When was the last time we had monster hurricanes, huge forest fires, gigantic earthquakes, and gigantic cracks taking place in the South Pole, all of which happened within the last 2 months? Think about that. We're hit now with hurricanes that are supposed to be once in a century, earthquakes that are once in a century, forest fires that are once in a century, cracking of the South Pole that's supposed to take place once in a century, and they're all happening even as we speak. So the question is there any rhyme or reason to any of this? Is it just bad luck? Is it global warming? Is it something in the heavens? I mean, what is behind this, if anything at all? And then we'll say a few things about the latest Nobel Prize in Physics. 3 physicists won the Nobel Prize recently for the discovery of gravity waves. Gravity waves were predicted by Einstein 100 years ago. And the question is, what does it mean for our understanding of the universe, the creation of the universe, where it all came from? Perhaps the secret of the Big Bang itself may be revealed in something called gravity wave detectors, which won the Nobel Prize for 3 physicists just the other day. First of all, as you know, we were hit with 4 major hurricanes. Hurricanes that lashed out at the great city of Houston, Texas. The Florida Keys, hitting Puerto Rico, Louisiana, Mississippi, whole cities leveled by these gigantic hurricanes in the Caribbean area. And the question is it linked to global warming? Well, yes and no. First of all, one of the main drivers of hurricanes is energy. Hurricanes have to feed off the energy of warm water. You see, warm water heats the air above it. Warm air rises, and then the earth spins beneath it, causing it to spin, and that creates a hurricane. So hurricanes are usually formed off the coast of Africa, and like a bowling ball, they sail across the Atlantic, creating larger and larger disturbances in the air mass until they hit the Caribbean and the Gulf of Mexico. And then, if the trajectory of this gigantic bowling ball is just correct, it can derive tremendous amounts of energy from the warm waters in the Gulf and the Caribbean, and then it becomes a monster hurricane. Unfortunately, these bowling balls sailed right through 4 times, creating untold havoc in the people that live in this area. So, is it global warming? Well, yes and no. First of all, there's no smoking gun. I repeat, there's no smoking gun. You cannot point to any one particular incident and say, aha, proof that it's global warming. You see, global warming is an average effect, that if you plot these things on a curve, you see a line that indicates that, yes, not only is the earth heating up, but the consequence of that is that more energy is driving the weather. And as a consequence, that's why, in general, on average, we're going to see more hurricanes. We're going to see more storms going into the end of the hurricane season, which is going to be in November. And because of this, there are other factors involved besides global warming as well. First of all, El Nino has something to do with it, not to mention the fact that there are cycles within the hurricane season. If you plot the incidence of hurricanes going back, let's say, almost a century, you find an oscillation taking place. Then in the 1960s and 1970s, that's when there was a lull in hurricane activity. And because of that, some people think we were lulled to sleep, thinking that hurricanes are no longer a problem. And that helped to create the real estate boom in Florida. Well, now the curve is tipping the other way, and some people think we could be headed for a very rough few decades in the next hurricane cycle. And again, that's just a theory, but it does seem to represent the cyclical nature of some of these hurricanes. But on average, if you take a look at the fact that the Caribbean is 2 degrees warmer than normal, that 2 degrees may not sound like much, but that 2 degrees warming is sufficient to energize gigantic hurricanes. So hold on to your hats, because there's an energy supply that is driving these monster hurricanes, and that is the warm water of the Gulf and the Caribbean. And does it have something to do with global warming? Yes and no. Well, several years ago on Exploration, I made a series of predictions as to what's going to happen when the Earth begins to heat up and the heating accelerates. First of all, we have the rise of monster storms and hurricanes, as I mentioned. Second of all, summer. Summer is on average a week longer than normal. Every farmer knows this. Every farmer has to adjust its growing cycle to compensate for this fact. And also forest fires. You're going to have more forest fires even as certain parts of the earth get wetter, because global warming is a misnomer. Global warming seems to indicate that the earth rises in temperature uniformly. That's not the way it works. Energy sloshes around like energy in a bucket. As a consequence, in one area, you can have a drought. In another area, you could have floods. In another area, you could have forest fires, all happening simultaneously because there's more energy surging around the atmosphere of the planet Earth. And some people think that that energy, in turn, is responsible for creating the tinder that is driving the massive forest fires that are now afflicting California. So far, 8,000 firefighters are battling the blazes in northern and southern California. 23 individuals have been killed so far, and it's going to rise in the future because of the fact that the flames are not under control yet. So we're going to see more casualties. We're going to see more deaths in the coming days. In fact, entire cities are aflame in California. People are literally running for their lives. Thousands have been evacuated, and 170,000 acres, think of that, 170,000 acres of land is in flames in California, and that's roughly the size of the city of Chicago. And that, of course, is going to affect the economy. Not only do we find that Florida oranges are going to be much more expensive as a consequence of the hurricane season, but the wine country, which is a tremendous income-generating area in California, parts of it have been wiped out. And so that's going to have another effect when it affects agribusiness. You see, California is in some sense the breadbasket of America. And because of the enormous amount of devastation caused by these forest fires, that's going to be reflected in your grocery bill in the coming months. And so this is going to have a direct impact on your pocketbook. And then I also predicted years ago that we would see a recession of every single major glacier on the planet Earth. And that prediction has come to be. We now have satellites that orbit the Earth that allow us to photograph the state of these glaciers. And we see that all the major glaciers, they are receding. And that, of course, is causing cracking in the South Pole, cracking that's taking place at an alarming rate as huge chunks of ice the size of the state of Delaware break off the South Pole. Then I said that we're going to see a rise in sea level. And this is not an academic question, because as sea level rises, it means that hurricanes have much more ferocity in terms of their surge, in terms of the flooding they create, because if the hurricane hits at high tide, it could cause massive flooding of cities. And then also I predicted that insects would start to go north. And we see that. Some people think that the rise of West Nile virus and other rather exotic viruses is due to the fact that mosquitoes can now go further north than they used to because the earth is heating up. Next, we have another series of disasters that are not linked to the atmosphere, and that is the disasters that afflicted Mexico. We had not one, but two monster earthquakes hitting Mexico. a 7.1 and an 8.1 2 weeks after that. Scientists now believe that the 8.1 earthquake was perhaps an aftershock of the earlier 7.1 earthquake. And it is also the earthquake of the century, the largest earthquake in 100 years. And it happened to the very day that the 1985 earthquake killed 10,000 people in Mexico. You see, the problem is that Mexico sits atop of not one, not two, but 3 earthquake faults: the Cocos Fault, the North American Fault, the Caribbean Fault, all of which are part of the Pacific Ring of Fire, which stretches from Latin America through Mexico, through California, through Alaska, down to Japan, a gigantic ring of fire that can easily sustain magnitude 7, magnitude 8 earthquakes. Now, believe it or not, magnitude 7 earthquakes happen once a month somewhere on the planet Earth. That sounds remarkable, right? And a magnitude 8 earthquake, like the one that hit Mexico last month, a magnitude 8 earthquake happens once a year somewhere on the planet Earth. Now, you may say to yourself, well, how come we don't see gigantic headlines screaming about the fact that we have magnitude 7 earthquakes happening every month? Well, that's because, for the most part, these earthquakes take place under the oceans. They take place in unpopulated areas, areas that don't have CNN television, areas that don't have a large population base. And as a consequence, we simply ignore the fact. We ignore the fact that the Earth is volatile, that the ground that you are walking on is not as solid as you think it is, but we're blissfully unaware of this fact because the media amplifies earthquakes when they happen in populated areas. And then, to make things worse now, we have 100-year cracks forming in the South Pole. A few months ago on Exploration, we talked about the Larsen Ice Shelf C, a gigantic chunk of ice about the size of Delaware that broke off. And now, just a few days ago, we had yet another piece of ice from the South Pole that broke off. This time, it was 4 times the size of Manhattan. Now, you realize that Manhattan is roughly 20 miles long. So imagine 4 times the size of Manhattan breaking off the Pine Island Glacier. In fact, the Pine Island Glacier is cracking up faster than almost any other glacier in the South Pole. Not to mention this, but we also have a mystery concerning the gradual breakup of the South Pole. This mystery is a gigantic hole. A gigantic hole has formed in the Weddell Sea, and nobody knows what causes this hole. This hole is not small. It's the size of South Carolina. I repeat, there's a mysterious hole that just opened up in the Weddell Sea, and it's the size of South Carolina. And unfortunately, we are clueless to explain why this gigantic hole simply opened up just recently. Now, of course, the likely suspect could be global warming, but it turns out that a similar hole opened up back in the 1970s. And so we think it may be periodic or it may not. It may have something to do with global warming or it may not. But it is a gigantic hole, one of the biggest holes on the surface of the planet Earth, the size of the state of South Carolina. And unfortunately, scientists are scratching their heads because we really don't know what is causing this latest anomaly in the South Pole. Now, there's a lesson here. And the lesson here is that we are still children. We are still scientific children when it comes to understanding earthquakes, when it comes to understanding the stability of the Antarctic. We can see that chunks of the Antarctic are breaking off. We can see that large parts of the North and South polar regions are heating up much faster than the rest of the planet Earth. But we're at a loss to explain exactly how this process plays itself out. So once again, the latest mystery is, why do we have this gigantic hole in the Weddell Sea, a hole that is the size of the state of Carolina? And then the next question people ask is, does this mean that sea levels are going to rise dramatically? Well, first of all, sea levels are already rising because the oceans are heating up, and warm water occupies more volume than cold water. And so the very fact that the oceans are heating up is directly responsible for the fact that sea levels are rising. However, these are ice shelves. They float on top of water. So just like when an ice cube melts inside your glass, it does not significantly raise the level of the water. The same thing here. It turns out that even though the ice shelves are breaking apart, this does not mean that sea levels are going to rise. However, the stability of the Antarctic is now being placed in question. Behind that, you have the ice sheets. And if the ice sheets start to flow into the ocean, then definitely you will get a rise in sea level. Also, I should point out that there's a bit of fake news out there concerning what I said about hurricanes and the disturbances in the atmosphere. There's a website that puts words in my mouth and says that I said that these hurricanes are in some sense caused by the military. Well, let's be very clear about this. The energy of a hurricane far exceeds the nuclear arsenals of the world, and therefore it's ridiculous to assume that Mother Nature can be tampered with by the military. However, there is a website that says that I said that these hurricanes in some sense are man-made. In fact, they're created by the military. Nope, I don't think so. I think global warming on average may be related to some of the resurgence in the hurricane season. But let's face it, it is not man-made in the sense that somebody deliberately created the hurricane season. Also in the news, the Nobel Prize in Physics was awarded recently to 3 physicists who pioneered the discovery of gravity waves. And so the question is, why should you care? Why is that important? How does that change our conception of the universe? Well, it was 100 years ago. It was back in 1915 that Albert Einstein came up with the theory of general relativity. But he wanted to test the theory, and so he thought that perhaps the simplest way to test it would be to see vibrations in gravity. And so he predicted a year later in 1916 that there should be something called gravity waves. So think of a pond. If you throw a rock in the middle of a pond, then ripples form, and these ripples make waves that expand radially from the rock. And so then Einstein said that, well, if the surface of the pond corresponds to space-time, and there's some kind of massive disruption of space-time, then ripples should form, which should be measurable. And that could prove his theory of general relativity. Well, then he did the calculation, and it was very depressing. He realized that in his lifetime, he would never see the ability to actually capture gravity waves in the laboratory. They were simply too faint. Well, it took 100 years. It took 100 years since that first prediction to actually find gravity waves in outer space. Now, the detectors that these 3 physicists built was gigantic. We're talking about something that's several miles across. 2 gigantic laser beams in the shape of an L. When there's a disturbance in the universe, a gravity wave from outer space hits the L and causes the laser beams to jiggle slightly. Well, these 2 laser beams are precisely in phase. But when a gravity wave from outer space hits it, they go out of phase, and you get spurious vibrations, you get interference patterns. And by measuring the jiggling of the laser beam, you can then calculate the nature, the magnitude, and the properties of a gravity wave from outer space. And again, when you do the calculation, you realize that even the sun, even our sun is not capable of creating monster gravity waves that can be detected on the planet Earth. What you need are black holes, colliding black holes, yet another prediction of Albert Einstein. So it turns out that, yes, black holes billions of light years in outer space. They collided, creating a gigantic disturbance in the fabric of space and time. And these disturbances rippled for billions of years until they finally hit the planet Earth. And that's when the LIGO detector detected them. Now, we should also point out that the Europeans, not to be outdone, the Europeans have their version of LIGO. Now, the American LIGO was the first to detect the gravity waves, but recently, when the European machine came online, it also was able to simultaneously track the very same gravity wave. Now, why is that important? Because then you can triangulate the direction where the black hole is located. Think about it for a moment. If you're sitting in the middle of a field and someone blasts a horn at you, you think, well, the horn sound came from that general direction, but you're not really sure. However, if you have listening posts stationed around where the sound takes place, you can triangulate. You can triangulate the sound to find out where the sound took place. That's what we do now, because we have not one, but two LIGOs. So given the fact that we had a collision of black holes billions of light years in outer space, the radiation took billions of years to reach the planet Earth, and will hit these two detectors at different times, slightly different times. That's how the GPS system works. Think about it for a moment. How is it possible that your cell phone can determine where you are located to within a few feet? That's because there's not one, not two, but 3 satellites orbiting overhead almost all the time. As a consequence, your cell phone is able to take messages from these 3 satellites, triangulate them, and then locate your position to within a few feet. So if you can find your location by triangulating with 3 satellites, you can do the same thing with black holes in outer space by having more than one detector on the planet Earth. And that's what they did. So the LIGO detector that the Americans have, the LIGO detector that the Europeans have now, is able to give us a triangulation of the location of these monster black holes. And what happens when 2 black holes collide? Well, they form a bigger black hole. That's right. They don't scatter. They don't break apart. They simply reform because of the enormous gravity and create an even bigger black hole. Now, what's the next step beyond this gigantic LIGO detector on the planet Earth? Eventually, we want to put them into outer space. Why? Because in outer space, you can build a detector that's not just a few miles across. You can build a detector that is 1,000,000 miles across, creating the biggest sensor ever created in the history of the human race to detect radiation not just from colliding black holes. No, we want to go beyond that. We want to detect radiation from the instant of the Big Bang, the instant of creation itself. This means that sometime in the future, we may have baby pictures of the infant universe being born. Wouldn't that be great? I work in something called string theory, and we hope that not only will we detect the baby pictures of the instant of creation, but we'll also see evidence of an umbilical cord connecting our infant universe perhaps to a parent universe. This is the multiverse idea, the idea that the Big Bang was perhaps caused by the collision not of 2 black holes, but the collision of 2 universes, or perhaps the splitting of a universe into 2 smaller universes. Now, remember that every time a new kind of telescope came into being, it revolutionized our understanding of who we are in this universe. For example, look at Galileo. About 400 years ago, Galileo turned the telescope to the heavens and opened up what we call astronomy. All the myths and fairy tales of the universe could be dispensed with your own eye. With your own eye, you could see that many of the teachings of the church were, in fact, wrong. The second revolution came when we replaced light telescopes, like with Galileo, with radio telescopes during World War II. Radio telescopes were perfected by the Allies as a forerunner to radar. But instead of detecting ordinary airplanes in the sky, These radio telescopes detected galaxies out there, colliding galaxies, quasars, infant galaxies. A whole new realm of telescope technology opened up with radio telescopes. Now we're talking about the third great revolution, and that is detecting not light waves, detecting not radio waves, but detecting gravity waves. And this, in turn, can open up a whole new realm of astronomy. In other words, light telescopes opened up the world of comets, meteors, and planets. Radio telescopes opened up the world of galaxies. With gigantic gravity wave detectors, we're now focusing in on black holes and the creation of the universe itself. This is amazing. Now, if you go to nasa.gov, you can see pictures of the Big Bang about 300,000 years after the instant of creation. You see a fireball. However, it's frustrating because you're seeing a picture taken roughly 300,000 years after the instant of creation. You're looking at the afterglow, the aftershock, the echo of creation. What we want is a baby picture of the infant universe as it emerges from the womb. We want to get detailed photographs of the instant of creation, not 300,000 years after creation. No, we want to get it to within a trillionth of a second of the instant of creation. And that's the promise of gravity wave detectors in outer space. The detector is called LISA, Laser Interferometry Space Antenna. It consists of 3 satellites that orbit each other. And in outer space, these 3 detectors shoot laser beams at each other. So think of a triangle whose sides are made of laser beams, and the 3 vertices are the 3 satellites. If a gravity wave from a distant black hole or the Big Bang hits this triangle, it'll cause the laser beams to vibrate. And that's the way we're going to detect gravity waves from outer space and gravity waves from the creation of the universe itself. So hold on to your hats, because what we are witnessing is the birth of a new technology, a new kind of telescope. Not a light telescope of Galileo, not a radio telescope, but a gravity wave telescope that could peer into the heart of a black hole and into the instant of creation itself. That concludes the first part of Exploration. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. In the second half of Exploration, we're going to rebroadcast an interview with a Nobel Prize winner, Professor Pollack, who won the Nobel Prize with the Intergovernmental Panel on Climate Change. In other words, the Nobel Peace Prize. And so we're going to talk about a world without ice. What happens when the polar ice caps melt? What happens when we have a massive disruption of the ecology of the Earth? What happens when sea levels begin to rise and inundate our cities? Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the second half of Exploration, we're delighted to have Professor Henry Pollack, a Nobel Prize winner. He was one of the lead authors in that paper from the Intergovernmental Panel on Climate Change that won the Nobel Peace Prize. And we're going to bring him on today. It's a pre-recorded interview with Professor Henry Pollack, who's a professor at the University of Michigan in Ann Arbor. And we're going to talk about his book, A World Without Ice. What would it mean if the poles begin to collapse? What does it mean if sea levels begin to rise? what happens if global warming runs amok? And so once again, we're going to be talking about worst-case scenarios. But once again, with us today is a Nobel Prize winner, Professor Henry Pollack, talking about a world without ice. And it's a world that you may not want to live in. Professor Pollack, how did you, as a child, first get interested in science?
I grew up during World War II, and every day in the newspaper there were maps of the front in Europe and in Asia and the Pacific, and I just grew very fond of maps and looking at the geography around the globe, and that, in a sense, I think is characteristic of all my adult research interests, trying to stand back and get a global viewpoint, not just of climate science, but in all the scientific endeavors that I've been involved with in a long career. I've always tried to get a global perspective.
And why geophysics, and specifically why the weather? Well,
I've not always been interested in the climate. I'm actually not a meteorologist, but my focus on the world's weather really is in the world's climate, which is the long-term average of what the weather gives us. And that's only an interest that has developed in the last 2 decades. Prior to that, I had done research in seismology, study of earthquakes. I've done work in taking the Earth's temperature to measure the amount of heat coming out from the interior and its relationship to earthquakes and volcanism. But in the last decade and a half or so, I realized that the rock temperatures that I had been taking for other purposes was also telling us something about what's happening at the Earth's surface. And we were able to reanalyze a lot of that data and reconstruct what the surface temperature of the Earth looked like for about the past 500 years, which conveniently takes us into the pre-industrial era. So there have been many transitions in my scientific interest. All of them, of course, are within the broad realm of earth science.
Okay, now let's talk about ice. Why is ice so important? Some people say, nothing but polar bears and penguins. Why ice?
Well, ice is important, and the number one reason that it's important is that it plays a big role in the global climate system. Ice is a white substance, and it's very reflective. And the more ice there is on the planet, the less sunshine warms the Earth because it is reflected directly back to space. With less ice, more sunshine falls on the solid Earth and warms us up. So the amount of ice is a very big player in how much sunshine the Earth absorbs. And the second reason that ice is important is that it's a very sensitive and unambiguous indicator of climate change, because ice on our planet is very close to its melting point. Small changes in the temperature cause very visible changes in the amount and geography of ice on the planet. And so it is what I call nature's best thermometer, because it is very, very sensitive to climate change. And then the third reason that ice is important, because as you lose it, important things happen on Earth. The first ice to go will be the mountaintop glaciers in the tropics and the mid-latitudes. And those glaciers today provide agricultural and domestic water to almost a third of Earth's population. That's a very large number of people who rely on that water for their well-being. And the other aspect, of course, of melting ice is that the water eventually runs into the ocean and raises sea level. It's not the only factor that raises sea level. The warming of the ocean water also leads to sea level rises. But sea level rising will, in simple terms, produce climate refugees. And that will be a very serious social problem as we displace people from the coastal regions.
And doesn't ice also help to regulate the weather? When we watch the weather in the evening, we see the jet stream coming from the Arctic. So doesn't all that huge mass of cold air also help to regulate the world's weather?
Well, it does indeed, and I would in no way minimize the importance of ice in our daily affairs as reflected through the weather. My emphasis has been on the longer-term trends, which we interpret in terms of slow climate change.
Okay, now let's take a look at the data. What evidence do we have that ice is thinning, that glaciers are receding, and what about ice cores that can take us hundreds of thousands of years back into the past?
Well, let's talk first about the evidence for ice receding. We have photographic evidence of mountain glaciers around the globe taken from the times when the camera was first available in the 19th century, more or less, that showed the position of ice in glacial valleys. And throughout the decades, and in fact throughout the 20th century, there are many repeat photographs of glaciers. And so you can just visibly see them receding in their valleys. So it's just visual photographic evidence of that loss of ice. Now, in the Arctic region, the sea ice, ice in the Arctic, is simply frozen seawater. We call that sea ice, and it's not very thick. It's on the order of 5 to 10 feet, sometimes a little more than that. But in the summertime, it tends to break up some, and then in the wintertime, it refreezes. But the extent of the summertime breakup has been changing dramatically in the last few decades. We have now only about half the area of sea ice in the summer that we had in the middle of the 20th century, and it's getting thinner as well. The average thickness of sea ice in the Arctic is only half of what it was a half century ago. And so we're faced with the prospect of perhaps an Arctic Ocean that is free of ice in the summertime in just a few decades. So that, too, is a very visible change. There, the observations come from satellites that can look down over the entire Arctic. Now, you asked about the ice cores. Ice cores are a form of sedimentary rock, if you like to think of it that, because they have layers that form each year from new snowfall. And as next year's snowfall falls on top of that, it compresses the layers underneath it into ice. And so we have a layer-by-layer, year-by-year history locked up in the ice. But in the case of the Antarctic, the record is almost 800,000 years long. And we are able to tease out of the chemistry of the ice, the temperature at which the snow fell at that given year. And another very interesting aspect of those ice cores is that as the snow is compacted and recrystallized into ice, it traps little bubbles of air, which are samples of the atmosphere at the time that the snow fell. And so we are able to chemically analyze the atmosphere year by year, going back almost a million years, to recover the concentrations of greenhouse gases in the atmosphere over long periods of time. What we've learned from that is that the concentration of greenhouse gases today is well beyond the range of natural variability over the past 800,000 years. The ups and downs that Earth's climate has experienced in the last 800,000 years have never gone as high in carbon dioxide as the concentration in the atmosphere is today. So it reveals that we're in the middle of a big inadvertent experiment with the chemistry of the atmosphere and its effects on the global climate that humans have just recognized and are now having to cope with.
And isn't it true that carbon dioxide levels and temperature levels in these ice cores are like two roller coasters in tandem going up and down almost simultaneously over hundreds of thousands of years?
You're absolutely right. That's a wonderful description of it. And what the significance of that is that the temperature of the atmosphere and the carbon dioxide content of the atmosphere are very closely coupled. And when one moves, it will pull the other along with it. And in the present day, what is doing the tugging is that we have increased the concentration of carbon dioxide in the atmosphere dramatically, and it is now pulling the temperature along with it. And that's, of course, what we're recognizing as global warming.
So let's now discuss the South Pole. We hear reports of gigantic parts of the pole breaking off the size of, let's say, the state of Rhode Island. Could you elaborate?
Sure, I could. There is a lot of ice on Antarctica. It has probably 90% of the global ice. And it is stacked up in places almost 10,000 feet thick and spilling off of the continent and into the sea and building up pools of ice called ice shelves. And these ice shelves are big. You mentioned the size of Rhode Island. Actually, the Ross Ice Shelf on the New Zealand side of Antarctica is as big as France. So these are huge pools of ice. And what we're discovering, what we're observing, is that these ice shelves are becoming unstable and breaking up and dislodging huge amounts of floating ice into the ocean currents around Antarctica. And this ice loss is at a pace that we've not seen before in human history. And so you're looking at instability. The understanding of what's causing it includes both warming, of course, from above, but the seawater is also warming and undermining these ice sheets from below and leading to their breakup. Once they break up, the glaciers that feed them from the interior no longer have a barrier in front of them, and so the glaciers themselves are now speeding up and spilling more ice into the sea. So we see the whole process accelerating as both the air and the ocean water are warming.
And speaking of a spiral effect, the tundra of Siberia is frozen, but as it thaws out, it releases methane gas, which is even worse than carbon dioxide as a global warming gas. Could you elaborate on the positive feedback if tundra begins to melt and release methane, which then heats up the Earth again?
Well, I certainly can. First, there's no question that the tundra is beginning to melt. There's a term called tundra travel days, which indicate how many days of the year you can drive across the frozen tundra because it is frozen. And that number, the tundra travel days, has been diminishing, and it's now measured in months, not just days, of reduction in tundra travel time. So there's no question that the tundra is softening up and melting. Methane is coming out. There have been measurements made in Siberia and in Alaska of the release of gases from the frozen tundra, and it does contain a great deal of methane, which is indeed another greenhouse gas, more powerful than carbon dioxide, but also it doesn't last as long in the atmosphere. So there is a little bit of a trade-off on that. But the amount of methane that is coming out, as I say, the measurements are just now beginning to be made, and the projections or the models of how this might proceed require that the tundra melt from the top down. And so it's a very slow process of diffusing heat downward into the permafrost. And I guess the good news is that process, while it will deliver quite a bit of methane, will be spread out over centuries and probably not be a catastrophic release of methane that would lead to an instantaneous enhancement of the greenhouse blanket.
Okay, now let's take a look at the worst-case scenario. Now, remember, this is the worst-case scenario. No one is saying that this is actually going to happen. But the worst-case scenario in 50 years and 100 years, assuming that governments do nothing, that is business as usual, population grows, economic activity grows. So again, with the caveat that this is a worst-case scenario, 50 years from now, what happens to sea levels? I'm in Manhattan right now. Yep. What happens to coastal cities? What happens to the bread baskets of the world? And then 100 years from now, what are your thoughts?
there are actually three time scales associated with ice loss. There's the decadal time scale, and in that period of time, the next 2 or 3 decades, we're going to see the loss of mountain glaciers everywhere in the world. We're going to see the ice-free Arctic Ocean in the summertime, and the issues associated with opening that up to commercial activity. So that's on the decadal time scale, the loss of mountain glaciers and the summertime Arctic Ocean being free of ice and open for commercial activity. On the century-long time scale, we're talking about losing ice in substantial amounts from Greenland and from West Antarctica. Antarctica actually has kind of two geographic regions, the West and the East. The East has the biggest pile of ice, and the West, a smaller pile of ice about the same size as Greenland itself. Now, both Greenland and West Antarctica, each one has the potential of about 20 feet of sea level rise. If we were to lose the ice from Greenland, sea level would rise 20 feet. If we were to lose the ice from West Antarctica, sea level would rise 20 feet. And any partial loss from both could also equal, many feet. So that is on the century-long time scale, and we're already seeing the early hints of that in the acceleration of ice loss from both Greenland and West Antarctica. Now, the big kahuna in all of this is East Antarctica, which has probably the equivalent of something on the order of 200 feet of sea level rise if we were to lose the ice from East Antarctica. But that ice loss, at least at the moment, seems to be on a millennial time, over 1,000 years or so. So that aspect of it is probably more delayed than in the future. But the 20th century alone could have several feet of sea level rise, and that will may have very substantial impacts on coastal communities everywhere. Well, coastal cities everywhere, of course, will be vulnerable to rising sea levels. And you don't need to have 10 feet of sea level rise to have a catastrophe. Just a few feet of sea level rise makes every coastal city more vulnerable to storm surges from what might in the past have been ordinary types of storms and hurricanes. But with higher sea level, everything is more vulnerable. In New York, of course, it's the subway system that is most vulnerable, because once water starts to encroach on Manhattan and the other boroughs, you're going to quickly find you have huge problems with the underground transport system. And there will be aspects of water supply issues that rising sea levels have on coastal communities that draw some of their water from the subsurface. And in areas that have a really flat terrain, such as the major river deltas of the world, particularly those in Asia, the Indus River, the Ganges, the Brahmaputra, the Mekong, the Irrawaddy, all of those have very flat terrains that just a few feet of sea level rise will lead to inundation many miles inland, and displacement of a great number of residents and loss of agricultural land.
And what happens to a nation like Bangladesh?
Well, that's a wonderful, I shouldn't say wonderful, but it's a spectacular example of a very flat country that will suffer widespread inundation and displacement of tens of millions of people. And it's, we have some experience with climate refugees in the USA following the Hurricane Katrina flooding of New Orleans. There we have had to address the issues involving 150,000 people. That will, it's such a tiny fraction of the numbers that will be displaced if we have a few feet of sea level rise in Bangladesh, where it will be in the tens of millions. The difficulties we had addressing climate refugees from Katrina will pale compared to the magnitude of the displacements from sea level rise the world over.
Okay, now let's take a look at some of the critics of this phenomenon, including physicist Freeman Dyson at Princeton. He has two criticisms. He, first of all, says that rising carbon dioxide levels is actually good for plants. Plants will thrive under that situation. And second, more serious, he says that we don't really know how much carbon dioxide is absorbed by the Amazon and by forests and by plants and by algae. And until we have a good handle on the recycling of carbon dioxide through plants, then perhaps these computer models are premature. What are your thoughts?
Well, let me address both of those. The first issue that plants will love it is kind of a facetious response, I think. It is true that carbon dioxide is the food for photosynthesis, and that green plants do take carbon dioxide from the atmosphere and metabolize and give us oxygen as a waste product. But it's not that plants need only carbon dioxide to thrive. They need the appropriate amounts of the right kind of nitrogen. They need water availability. And in many, many places and cases, carbon dioxide is not the limiting factor for plant growth. Moreover, it's not only the plants that we might want that will thrive. We'll also see many weeds that will also thrive, and in some cases overtake the vegetation that we might be seeking to enhance. The third aspect of it is that even if some agricultural production might increase, it won't always be in the same place that it was previously, because the temperatures are changing as well. And so we're going to see displacements, geographic displacements of agriculture, and that alone will be a social disruption across the agricultural world. So I think that far from being a blessing, some people say that it's a return to the Garden of Eden, but it will hardly be the case. There are many, many more factors than just the availability of carbon dioxide. Now, about his reluctance to do anything until we understand better the uptake of carbon dioxide by the forests of the world, I think that's short-sighted. The one thing that we do know is that the forests of the world are not able to take up as much as we're putting into the atmosphere, because the concentration of carbon dioxide in the atmosphere has been climbing. And as I mentioned earlier, it has climbed out of the range of natural variability of the climate system by a great, great deal. And so whatever the role of the green plants of the earth are, we're overwhelming them with carbon dioxide far beyond what they're able to take up, and leading to warming and melting of ice and rising sea levels. So I think that we don't have the luxury of waiting to see how the natural world evolves and how it may help in the take-up. I certainly endorse the idea of storing carbon in plants and in algae, and there are experiments underway for large-scale reforestation and for fertilization of the oceans. But none of these experiments that are underway have given us the promise that we have time to spare and we can wait and see how they work out. We really don't have that much time to spare, because the accumulation of carbon dioxide in the atmosphere is growing well beyond the ability of the natural world to pull it out.
And what do you say to the critics who say that it's just the sun? The sun is getting hotter. What are your thoughts?
Well, as a good scientist, the usual response is that, well, let's examine that possibility. Let's measure the radiative output from the sun across the full spectrum of wavelengths that the sun is sending energy to Earth. And the measurements of that over the last half century have actually shown that the sun's radiant energy delivery to Earth is slightly diminished. And if it was only the sun that was affecting climate, Earth would have actually been cooling some in the last half of the 20th century and the beginning decade of the 21st. But the measurements show that far from cooling, Earth is actually warming. So the proper way of addressing the causes is to ask, what are the likely factors, both natural and anthropogenic, and try and make measurements of each of them, assess their contribution. And when you do that, you quickly discover that the natural factors have fallen short in terms of accounting for the warming of the last half of the 20th century and that continues today. So the sun, of course, plays a big role in Earth's climate, and it always has. And we want to learn as much about the variability of the solar radiation as possible. But the extensive measurements that we have of that energy from satellites that are orbiting above Earth's atmosphere, so we don't have any atmospheric effects or detractions from it, it's showing that the sun has not been behind the warming that we're observing.
And some of the critics say that, okay, the Earth is heating up. They'll admit that now. But then they say that it's not human activity. It's a natural cycle. So do you have any, smoking gun that shows that it's human activity and not a natural thing?
Well, the first thing I would say is that I want to, make people who say that acknowledge that there is a possibility of a human signature first. And I'll give you an analogy that I used in that regard. I always ask, were there ever forest fires before there were people on Earth? And the answer, of course, is yes. We know that lightning can start forest fires, and it did that long before there were people.
Well, I'm afraid that's it for exploration.